not putting the averages because I think they're useless. Yeah, but who cares what the kata is? You need to do well.
Well, everybody who wants to go and something that's called they don't have their content actually do it.
Yeah.
AKA.
Sure. Not happening. Sorry. What? What? No. It's a dictatorship, not a democracy. Okay. Here's the plan for today. Today is a remarkable day because we're finally going to introduce Gaussian law, which is fun. Fun for me. Maybe not for you. But hopefully one day it will become fun. When I was sitting where you guys are in my electricity magazine class, I was just using that office, and the teacher was talking. His name was Mr. Clairvaux. He spoke with a heavy French Canadian accent, and I couldn't understand anything he was saying. It was my worst subject, and he talked about Gaussian law, and I thought it was the worst thing ever. But it's actually, after having studied it a little bit in order for me to teach it to you guys, it makes your life a lot easier. I'm going to attempt to convince you of that today, because Gaussian law will make life easier, right? But it's subjective, I guess, because you have to test it on it, there's a reason how to test it on it. Your functionality is on its way. Before I get to Gaussian law, though, I need to review a little bit what we did last time. That's what we're going to do for the first half of the class, is we're going to do a review. And then in the last half of the class, we'll do Gaussian law. For this review part, I'm just going to go over just a few concepts, very simple concepts. And then I'm going to get you guys to the problem with these groups. Okay, so however many groups you want to make, however many people, that's good. As long as one, everyone is working. All right, everyone, no one's slacking. And two, no one's working alone. Okay, teaching this stuff to someone else or having it being taught to you some other way is the best way to learn. If he tells you guys like I'm some kind of president of this thing to you, doesn't mean much. All right, you guys need to talk about it. You guys need to make it make sense for yourself. So I want you guys to practice in groups. Right? Even when you're studying for your test and your exam, studying in groups is always better. Yes, you need your alone time, but having a part of that studying with a friend or a partner, always. All right. So let's get started. It's review. And just to remind you, we're talking about electric potential. I have here what? What is this a picture of? Electric field? What did you say, Julien? Equipotential lines, not electric fields. I didn't put the electric fields. What do we know about electric fields and how are we supposed to draw them when it comes to equipotential lines? Linear? Perpendicular, very good. And remind me, which one's a vector, potential or electric field? Okay, and therefore it has that direction. Okay, good. So if I were to draw electric fields that were perpendicular to my equipotential lines, I can attempt to do that, and it would look something like, oh, like this maybe. Whoops, not without that blip, of course. It would look like that. And look at that. It's, oh, you guys don't see it very well, eh? Let me switch colors. All right, look at that. My electric field line is perpendicular to my potential, equipotential line. I need to give it an arrow because it's a vector. Which direction does it go in? So towards the Q1 or away from Q1? Away. So Genevieve says away. Is there enough information here to determine that? Yes, there is. So over here, what does it say? That's, it's becoming more and more negative. So that means Q1 has to be negative. And when we draw electric field lines, do they go towards the negative or away from the negative? Towards. So they go in this direction, like that. So I can draw a whole bunch of these.
This is essentially what your lab is. Something like that. All right. As long as it's perpendicular and as long as the direction is right, I'm happy. Oh, no, that one is going to be positive. You're absolutely right. Okay. There's your little review. And here's your answer. The electric field at all the different points on this map. That's if you were to individually calculate each one of these as a point, you would see that the electric fields look like that. And remember, if you want to calculate the electric field at, let's say, this point here on the top right, then you have to do the electric field based on this charge, and based on this charge, based on this charge, and based on this charge, right? And then add up all the vectors, and then the total resultant vector will give you something that will look like for the total vector. If you do that for every single point on this page, then you get all the electric field lines that exist. There is an infinity number of them, so I'll let you decide one is enough. Okay? You guys okay with this? Does it matter whose eraser is which? Okay, good. All right. So the objectives are the same as last class, for you guys to understand the difference between equipotential lines and potential energy and so on and so forth. Just as a reminder, the electric field depends on space and allows us to compute that electric field or the force on any charge, right? So that's why it's the force per charge. And similarly, the electric potential is the amount of energy per charge, okay? So there's that relationship that you need to remember, okay? Here you have what we talked about. You have those slides. You don't need to type them. Yep. Here we have the equations that you guys are going to need to use. All right, there's one little mistake on this though. Here it says delta V is equal to KQ over R squared. That's not true. It's just V. Remove that delta. The voltage is equal to KQ over R squared. KQ over R, not squared. Yes. Sorry. Yeah, the first and second one are the same one. They're just rearranged. And it's representing the relationship between voltage and energy. Yeah. Charge and distance. All right. Do we all remember this? The units for energy is joules, units for voltage is volts. Pretty similar, pretty simple. There's scalar quantities. This is so important for today, okay? Please understand the difference between scalar and vectorial, okay? And here we are, my first example. We'll do this one together, and then I'm going to let you guys work on the rest on your own. So the question's asking you, at this point P, what is the potential? And then we'll deal with letter B afterwards, but I want you guys to focus on A first, okay? So A would be, how do you find the potential? Well, the total potential of a point, at that point, right? So V total is going to be equal to the potential from this charge plus the potential from this charge. So it's going to be V1 plus V2. And let's call this one Q1, and we can call it Q2. So therefore, this is R1, and this is R2. It's simple. It's V total is equal to KQ1 over R1 plus KQ2 over R2. I have a challenge for you. Does anyone care to do a challenge? Yeah? Where are my nerds? Come on. Try to do this in your head. Try to do this calculation in your head. No calculators allowed. this mental math, right? Yeah, Gabriel. Absolutely. Did you do it? In your head? What did you get? Close. You added instead of subtracted because one of them is a negative charge. So, minus it. Okay? 135. Is it in your head, Raza? What was your trick? It's just simple. Your 10 to the 9 and your 10 to the minus 9 are going to cancel each other out, right? And the same thing on the other equation. Your 10 to the 9 and your 10 to the negative 9 cancel each other out, right? And when you divide by 0.05, that's the same thing as doing what? Multiplying by 20. And the same thing as dividing it by 0.04 is the same thing as multiplying it by. Think about how many quarters there are in a dollar. There's 4, right? So 4 times 25 is equal to 100. So that's the same thing as multiplying it by 25. Yeah. For a negative charge, yes. And when you add them up, well, it depends which one's stronger and which one you're closer to. Okay? You all understand why I got, or how I got 135? Whether it was a calculator or not? Okay. Now the second question is, how much work must be done on a proton to bring it from infinity to this place? The question is very abstract because it's asking you about bringing a charge from infinity to a certain point. It's a really weird question, but it's very simple in nature. What's the potential energy of a charge located at an infinity place? It's 0 because it's 1 over r, so it would be 0. So the potential is 0, and you bring it to a potential of 135 volts. So if you're looking at it, work is equal to charge times delta V. Right? Did I do that right? Yeah, exactly. And your delta V is 135 because it was at 0 and now it's at 135. So your delta V is 135. And then you multiply it by the charge, which is a proton. We know it's 1.6 times 10 to the negative 19 coulomb. Can someone do that in their head? Raza? 1.6 times 10 to the 19, negative 19 times 135. I'd be impressed if you could. This one is, there's no trick to this one other than just doing it. What are the units? Joules, exactly. Can someone give me a number? Very good. Okay. Everybody's okay with this? Questions? Okay, so for the next ones, I'm going to give you guys, it's 125. I'll give you guys until 2:10 to answer everything up until and including example practice 4. So it's practice 1, 2A, 2B, 3, and 4. Okay, try to do all those. I'll give you guys until 2:10. Please work on this in partners, all right? Even if it's just one other person, definitely don't work on this on your own, okay? Okay. So, gases law. Thank you, Yusuf. Have a seat.
God damn it, I got trolled.
You got the last word. Let's go.
Ouch.
We're going to talk about Gauss's law, and he's going to become a favorite of yours, I hope, because otherwise, without him, we would have to be doing some level of math that you haven't learned yet. But we need to gain an appreciation for Gauss, because if we don't, then we don't know what we're missing. We don't know how hard things are if it weren't for the scientists to come up with these approximations. Okay, so to do that, for you guys to appreciate a little bit what he does, we're going to do an example. And the example is going to be about finding the electric field at a point P above a ring. So here I am, here's my ring. And a point P, all right, is going to be where I'm going to try to find the electric field. Okay? So you guys are looking for slides, it's not there. First of all, you can open up PowerPoint 09, because I'm done with 08 now. Open up 09, and I just added a blank slide now so that I can write on. All right, so later on, you guys are going to get this. All right, so if I want to find the electric field at point P, it's very easy. No, not really. If I were to take a point on this circle here, on this ring, remember it's a ring, it's hollow, it's totally hollow, it's infinitely thin, and it goes in a circle. I drew it kind of like an angle because I'm artiste, you know how I do that. And this point P is at a height h from the center of this ring, all right? And this ring has a radius, capital R. And therefore, this distance here, we're going to call this little r. Okay? And I'm just going to erase my little point P there because I don't need it. I want to point your attention to this angle here. And that angle, we're going to call that theta. Okay? If I were to say that this is a positively charged ring, right? What is the charge of that? Is it positive or negative? Positive. Okay, perfect. And therefore, what kind of electric field is this dot going to feel from that point on the ring? Repulsion, which means that it's in which direction? That direction. Okay, so let's write that. So this is going to be my DE, my electric field from one point, from that one point on the ring. Yes. The point at the top, this is a location. It's not charged at all. Okay, so remember that's the difference between force and electric field. All right, so I have that distance, and I also want to point your attention to another thing. If I were to continue going upwards like this, right, what would you say about this angle? It's also theta. Okay, very good, thank you. All right, and lastly, as I'm going to make life so much more complicated afterwards, if I were to take a point here on the ring, exactly opposite of the other point, all right, it would also have an electric field in that direction, right? You guys agree with that? And if the ring is uniformly charged, then that electric field will be exactly the same in magnitude as the other one, right? So these two arrows should be the same length. Let me redraw that so that it's more clear. All right, those two arrows are the same length. But which component of them cancel each other out, x or y? X's cancel each other out, so we don't give a crap about the x's. We only care about the y's. The total electric field is going to be pointing upwards no matter what, because all these points along this circle are going to have another point opposite from it on that circle to cancel it out. Okay? Are we good? All right, so if that were the case, then I don't even need to consider the x-axis. So what I need actually is, now I'm going to erase all this. This, and this. All right, this is still h. And what I need is this thing here called delta or DEY. So it's the small electric field felt at that point from the 1dq on this ring, all right? And it's going to be upwards because later on, once I integrate everything, there is going to be another one that's going to cancel its x component. Okay? Everyone's following so far? Let's get mathematical. It's the electric field that I want to calculate. Up until now, your problems that you've had to do, they were all determine the charge. And that was hard already. And now we're finding the electric field, and this is going to be even more hard, right? If you remember, the electric field is, K, Q, but this time because we're using DEY, so that means it's going to be DQ over R squared. It's not finished because my DE is only of the y-axis. So which means that I need to add a cosine theta to make it so that I only consider the y-axis. Right? Wrong? Maybe? Yes? Yeah, Neil. Remember, those of you who are confused, this is DE, and this is DEY. Therefore, this is the angle, and that's how I multiplied. That's why I multiplied it by cos theta, so that I can get this DEY. Yeah. Cosine is for adjacent. So what's adjacent to that theta? It's the y-axis. Yeah. Okay. Okay, perfect. Let's move on. This is a line, right? So remember, a ring is a line that you just turned around itself. So that means I need to use linear charge density. What was the symbol for that again? The upside down y, yeah, lambda, exactly. So lambda dx over r squared cosine theta. If I were to look at a circle from the top, pretend that that's a circle. And this circle has a radius r. All right. And I'm telling you that this distance here, the distance that I have highlighted there, I'm telling you that that is what I call dx. And that's a circular length. It's not a straight length, it's a circular length. We call that arc length. You guys learned arc length? If you didn't, now is your official introduction to arc length. All right? Now, this arc length is defined by this angle here, d theta. Okay? Because it's a very small arc length, we're therefore going to have a very small d theta. Okay? So we can redefine dx as the radius multiplied by d theta. That's the definition of an arc length. And I could replace that in my lovely equation over here. So dEy is equal to k lambda r d theta over r squared multiplied by cosine theta. Yeah. I'm sorry. We haven't gotten there yet. Okay. We could also replace the r squared because r squared is not really a real defined measurement, right? It's really only, r is really only a distance that's defined by capital R, the radius of the ring, and the height of the point. So let's redefine r squared as the square root of capital R squared plus h squared squared. So I can remove the square root, right? So I'm just going to end up with r squared plus h squared, right? You guys see how I changed my little r to this from here to here? Remember that r is the hypotenuse of this right angle triangle. And the hypotenuse is r squared plus h squared and square root of all that. But because I squared it, I removed my square root. Okay? I could also change my cosine theta. Cosine theta is what? Adjacent over hypotenuse, right? So in this case, adjacent is what? Oh, adjacent of that angle is h. And my hypotenuse is, again, r squared plus h squared. This time, the square root of it. And the square root is the same thing as putting something to the power of 1/2. You guys follow my logic? Okay, good. So now let's simplify everything. So we'll integrate now, actually, and I'll tell you what the limits are going to be. So EY is equal to, let's take out all our constants. So it's going to be K lambda R H over R squared plus H squared. When I multiply two of the same thing, different exponents, I can add the exponents. Remember that? So this is going to be to the power of 3 over 2. Yes? Yep. Lequel? Dans la première ligne? Dans la diagonale? Après le lambda. Oui, tu as raison, c'est R majuscule. Here it's capital R. Sorry about that. Tu as raison. Merci. So all these are constants, and now I write my integral sign, and all I'm left with is d theta. And I'm trying to integrate all around the circle. So the limits of my integral are going to be from 0 to 2 pi if I'm using radians. If I'm using degrees, it would be 360. Okay? So it'd be 360 if I wanted to use degrees. You can use both. You'll get the same answer. Just check what your calculator mode is in. All right, so now that means that, what's the integral of d theta? What's the integral of d theta? It's theta, right? So I'm left with k lambda r h over r squared plus h squared to the 3/2 multiplied by theta from 0 to 2 pi, which is exactly just all those numbers multiplied by 2 pi. So it's going to give me my final answer. Come on. 2 pi k lambda rh over r squared plus h squared 3 over 2 to the power of 3 over 2. Ta-da! Done. Only after all that work were we able to determine the electric field at a point P above a simple shape like a ring. There. All right? All that work. This was the easiest possible example that I can do with you, and also the hardest because after this, you don't have the math necessary to solve a more complicated shape. But it doesn't mean we're not going to try, because I like to scare you guys. Can I move on? Yes. You can use both, but yeah, radians is probably more simple. Okay, so let's do this a bit more complicated. This time, I don't have a ring, I have a disc, and this is a full disc that has a center and everything, okay? So this disc is made up of, let's call this radius, R, and we're trying to find the electric field at point P that is located at height h above the center of the disc. And this distance here We're going to call that R again. So far, everything is the same, except just please keep reminding yourself that this is a solid disk. All right? Not a ring. So if you want to go back on them, the other one you write ring, you can do that. This one is a solid disk. All right, so that means that I need to find the electric field at that point P of every single ring and every single degree. All right, so that means that, let's say I took a ring, a randomly small ring that's in the center of this disk, right? So imagine this disk is made up of an infinite number of small thin rings that are stacked inside one inside each other to make this whole disk. Imagine that, right? Imagine how oddly satisfying it is when you drop this and all the rings fall into place. Life is good, everything is zen. The way to find the charge of that, so we have to find the charge of that one ring, right? And then we did all that work to find the charge. So let's start the same way as we did before. So dq is equal to sigma. My sigmas are ugly. I haven't mastered the art of sigma yet. Sigma dA. Okay? Keeps doing that, sorry. The sigma I'm going to keep there, but I will change that dA. How do you find the area of this one, and careful about which words I'm using, the area of the ring, not the disk, of that ring. Now, one of these thin rings, how do you find the area of it? Danielle? No, you don't need that. What's the formula for it? It's the circumference, close, times the thickness, which is what? Exactly. So it's the circumference multiplied by its thin thickness. So 2 pi r, that's the circumference, multiplied by d. I'm running out of variables here. Guys, bear with me for a second. I'm changing the diagonal from there. I'm going to change that to x, okay? Just because I'm going to use the dr for this. But it doesn't only depend on the radius of the ring. It also depends on, because we're only taking one part of that. I'm only taking one part of that ring, so I have to make sure that I incorporate that radial thing as well. Oh, I forgot to put the over r squared, eh? I forgot the k. Oh, guys, I forgot a lot of stuff. Over x squared. I forgot the k and over the x squared. And so I'm putting the k again, and over x squared. And in this case, x squared is just r squared plus h squared. And this is where I want your logic to let go a little bit, okay? So it's great that you can understand it up until here, but you really do need the next level calculus in order to be able to go to the next step. And I also made another mistake, guys. I'm really sorry. It's not dq, it's de. Oh boy. And if we want dey, what do we need to do again? Yeah, so let's just add that now. Same thing, cos theta. And it not only depends on that radius, like I said, it also depends on the radial arc length that we talked about. So we're going to have to talk about that. So dey is equal to k sigma 2 pi r, which is no longer just r anymore. Now it's capital R d theta dr over r squared plus h squared. All that multiplied by cosine theta, which we said was h over r squared plus h squared square root. Yes. I replace this r by r d theta. That's the part of the math that you guys are missing. That's why I expect understanding to go out the window at this point. All right? Okay, so have you ever seen that an integral as a function of 2d's? So if I wanted to solve for EY now, I have to do the double integral of k sigma 2 pi r d theta dr h over all that over r squared plus h squared to the 3 halves. All right? And the limits of my two integrals are 0 to 2 pi for my d theta. What are the limits of my integral for dr? 0 to r, so the capital of k. Now, no, you guys haven't learned this in calculus yet. It's not an integral of an integral. It's something called a double integral. Now, put your hand out for a second. There's a lot of you speaking at the same time here. Just because you don't need to know how to do this, you still need to know what this means. Okay? The reason why this is important is that there are two variables here to take into account. All right? It's not just a function of the radial distance, it's also a function of the little r, because all of those are going to give a different distance to my point P that's going to have an electric field going upward. Okay? It's unfortunately not that simple, and therefore we have to use this more complicated math. Because of Gauss's law, we won't be able to do that. We won't need to do this, okay? So automatically, you should thank Gauss that you don't have to do Cal 3 before doing electricity and magnetism. No, what you need to understand is it's complicated AF, all right? Yes? The, where? That would be the arc length. The arc length. You guys confused yet? Good. Incoming Gauss's law. What's going on, guys? If you let me speak, I could explain it. Justin, Danielle, if you're not interested, go away. Thank you. All right. So introducing Gauss's law. And automatically you're scared because holy crap, what are those symbols? There are three symbols here you don't understand. I bet you only think there are two, but there's actually three. That, you guys know what that is? Okay, that's the first one. This is phi, and it stands for flat. Phi is another Greek letter, P-H-I. That's the first symbol that you guys need to understand, and we're going to talk about that just right after this explanation. This here is a strange integral sign that kind of looks like the treble symbol if you're into music. It's not the treble symbol if you're into music. It's called a surface integral, all right? And I'll explain that in the next couple slides. It's also not complicated. What's the third symbol that you guys are not familiar with? That's just a constant, so that's not it. It's that. What is that? It's not a times. It's something called a dot, or dot product. Okay? The dot for the dot product is bigger than the dot for the multiplication. And I'm kind of I'm spoiling your linear algebra class a little bit because you'll be learning about dot products with Mr. Zentner. But it doesn't mean we can't learn it now. It's very simple. It's not that hard. Let's talk about flux. All right, here's your guy. Here's your man. Gauss is talking about flux, which is, I will define it right now. Flux is, imagine this for a window. Okay. sheet of paper as a window. That's what you do. And electric field is going into this window. The amount of electric field that goes into this window or this area is considered to be flux. To make this window bigger, and I send electric field lines into it, right? The flux is bigger. Think of it as a pipe. The wider the pipe, the more water flows through. The narrower the pipe, the less water flows through. Okay? So right now, there's a whole bunch of flux going, there's a bunch of electric field lines going into this, generating something that we call flux. Okay? It's just a definition of flux. It's electric field multiplied by area. And that was kind of what Gauss's law was saying. If I were to turn this window and for it to be totally on its back like this, and again, it's a window, and the current of electric field is going in this direction only, what is the flux through this window? Zero. Okay, that's really, really, really important. Did I change the area of my window? Okay. Let me ask you another question. The way you've learned it up until now, is area a vector? It is now.
What?
Yeah. All right. This is the same area. No matter how you orient it, the magnitude of this area is always the same. However, if I had it like this, or if I had it like this, those are two completely different things, and the only thing that I'm changing is the angle of my area with regards to the electric flux. So there's a definition for an area vector. Imagine this is the surface of your area. Out of that surface, there is a unit vector coming out. Let's call this r hat. You guys learn r hat from a linear class? Okay, let's just call it anything, whatever. It's a vector. All right, and this is the magnitude of the vector is going to be the size of my area. The direction of my vector is going to be defined by a perpendicular to the surface arrow. Okay, so let's say this is about 20 centimeters by about 30 centimeters. So this is about 600 centimeters squared. Right, so the magnitude, no matter how I have it oriented, is 600 centimeters squared. And based on this, there is a direction defined to it now as well. Okay, so it's going to be 600 meters squared in Yusuf's direction, for example. Okay, or in Sammy's direction, or in Annabelle's direction. Yeah. Well, we have to talk about this in 3D, but you'll see ultimately everything is going to fill in nicely. Okay, but this is a concept that applies only in 3D. Okay, so now, tell me one thing. This is the maximum flux. When the electric field is coming this way, this is what the area needed to be oriented. You guys remember? What is the angle between electric field vector and my area vector? 0 degrees. What is the angle difference between my electric field vector and my area vector? 90 degrees. So which trigonometric relationship can I make it so that it's maximum at 0 degrees and minimum at 90 degrees? Yes? Close. What's the sign of 0? Cosinus. All right, so let me go back to this here. We said that the electric flux is equal to the electric field dot product the area. All right? And if we define a vector for that area, we can say that the electric flux is equal to the magnitude of the electric field multiplied by the magnitude of the area multiplied by cosine theta. And cosine theta being the angle that separates the electric field and the area. Now, if you get this is when it's at its maximum. I guess. If you say that this is its maximum, then cosine of 0 is giving you what? 1. And if it was like this, and this is at its minimum, the cosine of 90 degrees is 0. So you can't multiply anything more than 1 on the unit circle, and you can't get anything if you multiply it by 0. Does that make sense? Do you have a question? You have a question? No? That's what a dot product is, all right? So a dot product is you take two vectors, you multiply their magnitude and the angle between them, all right? There is an actual more linear algebra definition of it, which has to do with projection of the vector onto another vector. So imagine, you guys want me to tell you or do you not care? Okay, I'll take that as you don't care. All right. Just when it comes in linear algebra, come back and mention to me how cool it is, if you actually think it's cool. So there's your man, Gauss. Look at what he looks like, because I'll test you on what that is. And we're going to talk about Gauss's law now. So again, coming back to this, he says that flux, this thing called electric flux, is the dot product of E and A. So you have the flux going over a certain area. Flux is defined, your electric field is defined as we learned it. So newtons per coulomb, it has a direction, et cetera, et cetera. That's exactly what you guys know from before. And area is defined by literally the area in which the flux goes through. Yeah. It's equivalence. 3 lines means equivalent. Yeah. If I increase the area, am I increasing the flux? If I increase the area, am I increasing the flux? If I increase the electric field, am I increasing the flux? Okay, so it's a direct proportionality. Leo, you had a question? You good? Yeah. At the bottom? So this is a dot product, and I converted it into a regular multiplication. Yeah. There? That's a dot product. We'll talk about why it's just a multiplication in a second. All right, it's a part of Gauss's law. Okay, here's a question. I'm not asking you to answer this question because you can answer this at the end of class maybe. So imagine you have a wire. All right, everyone's imagining this as being a wire. This thin cylinder is a wire. You zoom in, it kind of looks like a cylinder, but imagine it straight line, and that's it. Okay, so I have a straight line, and that's it. And this cylinder here, I'm going to henceforth refer to this as a toilet paper roll. Okay, imagine it's an empty roll of toilet paper. It's infinitely thin. It's hollow. It's got nothing on either end. Right, and this we're going to, in a physics term, we call that a Gaussian surface. And you might ask yourself, what the F is that? Well, we haven't decided that yet. We haven't learned that yet. So it's going to be toilet paper roll for this slide. If I were to cut this wire and look at it face on, right? If I were to cut this wire and look at it face on, and this is a positively charged wire, what would the electric field look like coming out of it? Okay, you want to actually tell me? Radially outwards, very good. Okay, radially outwards. Now, if I were to look at that roll of toilet paper from that same perspective, okay? So here's my roll of toilet paper that's around my cylinder there, all right? And I'm looking at it, I cut a cross section out, I'm looking at it. Which direction are the area vectors, the surface area vectors of this cylindrical shape? Yeah? Radially outwards? Yeah. So there's your A vector for that point. There's your A vector for that point. Your A, your A, your A, your A. Yeah. It's because this is a hollow, it's like a toilet paper roll, there is no end, right? And remember, the area vector is when there is a surface. If there's no surface, there's no area vector. Okay? So imagine that you have your toilet paper roll. Right along this surface, all the area vectors are pointing upwards. If I rotate it, it's just that one. It's basically radially outwards on a surface like this. So at any point along this wire, along this wire. We can make this an infinitely long wire. If we have an infinitely long toilet paper roll above it, will the electric field and the area vectors always be parallel? Yes or no? Yes. Yes. The answer is yes. So at any point along this toilet paper, at any point along this wire, wherever there's a field line coming out of that wire, there is an area vector on that toilet paper parallel to it. Okay? So that at any point, at every point, so if I said that the electric flux is equal to E times, or sorry, let me erase that. This is from the first slide now, that the electric flux is equal to this thing called a surface integral of E multiplied by dA, or not D multiplied by, but dot product dA, and that at every single point, this angle between the two is 0, so then it's always just going to be E times the surface integral, which is basically now just the surface area, right? So E times A. And no need for cosine theta, because every single electric field line coming out of that is parallel to every single area vector coming out of the toilet paper roll. You guys follow what I'm saying? Yep. Surface integral. Okay, so it means that you add up all the points along the surface to make up the full surface. So if I add up all the small dAs for this toilet paper roll, then I end up with the area of the toilet paper roll. Okay? So this is super duper important. Now we know that if I pick a surface appropriately enough, right? If I made my Gaussian, so this is the choice that you have, and it's a choice that I want you to always make the correct one. If you choose your Gaussian surface to be appropriate, then your calculation becomes a lot easier. You chose it. You chose to calculate the flux coming out of that toilet paper roll. You chose to calculate the flux coming out of that toilet paper roll, and that's a fantastic choice because now you can generalize and say the flux, come on, the flux is equal to just E times A. And that's a very simple calculation to make. You have the number for the electric field, you have the number for the area, you determine the flux. Yeah. In the case of a wire, it's not always going to be a wire, and we're going to see another example of it. Okay. Next. Now when I wanted to switch slides, it doesn't switch slides. What is it? Switch. Okay, here we go. Let me skip this and I'll come back to it. Yeah, I'm going to come back to that other slide in a second. Let's come here for a sec. And we're going to do the same thing. In the last example, we had a charged wire that had an electric field coming out of it. Here, instead of a wire, I have a charged sphere. This is a sphere. You can consider this to be a point, or you can consider this to be a sphere. If I had to choose a surface to go around this such that all of the electric field lines will be parallel to all of the area lines of the surface that I picked, what kind of surface will I pick? A sphere, absolutely, and that's what they did here. So they took a sphere, and any point along this sphere, or let's even get more simple than that, at any point on this dot, there is an electric field coming out radially outwards. And at any point along this sphere, so let's say we chose now this electric field line, there is also an area, and that area is parallel to the electric field. And we chose a really amazing Gaussian surface to calculate our flux. All right, so in this case, again, we can say that the flux is equal to E times A, because at every single point along this surface, the electric field and the area are parallel. That's the really most important part. Okay? So far, so good? Skip slides. Okay, now we're getting to what we call the second part of Gauss's law, and this is the most important part. So he not only said that the flux is going to be equal to E times A if you picked your surface correctly, he also said that it's equal to Q inside divided by some constant called epsilon naught. Okay? And just for your information, epsilon naught is 1 over 4 pi k and is equal to 8.85 times 10 to the negative 12 complicated units afterwards. Okay? I want to ask you guys for a problem now. Let's say we have some point charge, positive point charge, and I determine that I want to figure out what the electric field is at some point. So this is my positive charge, and I want to find out what the electric field is at some distance r away from it. You guys will say, easy, electric field is equal to kq over r squared. Yep, you're right. But how do we get that? Well, that's where this comes in. So we have a point at distance r. If I picked another point at a distance r, what's the electric field at that point? Is it the same as that one? Yeah, all right. It's the same one. The direction might be different, but it's the same one. So I could pick a Gaussian surface that is spherical around this point charge, and at any point along the surface of that sphere, my electric field is going to be equal. So I'm going to pick my Gaussian surface to be a sphere around this point charge. Good grief. And so that I can say that now, if I'm using this equation at the top, my electric field, which is what I'm solving for, multiplied by the area of my sphere. What's the area of a sphere? Cubed? It's a surface area. It's not cubed. Squared, exactly. So E times 4 pi r squared. And I chose r because that's the distance at which I drew my Gaussian surface. I chose that because I'm smart. Is equal to Q inside. So Q inside is whatever the charge is inside of my Gaussian surface, divided by this constant epsilon naught. And if I'm solving for electric field, well, I just need to isolate it, right? So Q inside divided by 4 pi epsilon naught r squared. What's 1 over 4 pi epsilon naught? Yep. So therefore, this is going to be equal to kq inside divided by r squared. That's how we came up with that relationship. See how easy it was to calculate the electric field of a point outside of a point charge? It was easier because it was an easy object before. But now we have a way to solve it for literally any other object. Let me ask you guys another question. The flux depends only on what? The charge. That's it. The flux depends only on charge. That's a constant. So that's interesting, because if we looked at this, now we're going to go back to this here. The flux coming out of this surface, what's the charge inside of this Gaussian surface? Q, so the charge is going to be that Q divided by epsilon. What if I chose this as a Gaussian surface? Or if I chose this as a Gaussian surface? It doesn't have to be a sphere. It doesn't have to be any shape at all. As long as the charge inside is inside, what's the flux coming out of this? It's what? It's the same. It's always Q over epsilon naught. Okay? It really just deals with the charge in the inside. Does the charge have to be in the middle? No, it has to be in the inside. That's the only definition of it. Okay? So far, so good? Mm-hmm. By the way, this is the last major topic before the test. Okay, so this is all included stuff. When's the test? The 28th for you guys.
Okay, so
I'll talk about the test once we're done everything. All right, so here's the full equation again. It's the integral, or the surface integral of dA, right? And if you choose your A properly, if you choose your Gaussian surface properly, you can make this just equal to regular E times A. I don't know if you guys can see it, but it says equals to E times A. It's equal to E times A. Okay? That's if you choose your Gaussian surface correctly. Here's a question. What's the flux through my weird shaped Gaussian surface? I'm asking you what the flux is. What does the flux depend on only? The charge inside. Yep. So the flux here is going to be E, 8.85 times 10 to the negative 12. All right, perfect. Super easy stuff, right? Moving on. Here's another problem. This here, I have a positive Q in there. What's the flux coming out of this Gaussian surface here, this dark tan colored thing? Q over E. What is the flux here? Minus Q over E. What is the flux here? What's the Q inside of this Gaussian surface? It's what? There is no charge inside, therefore the flux is, but there is electric field lines coming in. It's just that they're also going out, so they cancel each other out. Anything that comes in a closed surface, and if it goes on long enough, it's going to come out of that closed surface. That's life. That's the way it is, right? So electric fields go in, they come out, total flux zero. That's it. Boom. No charge inside. What's the flux inside this whole thing? Ibrahim. Which part? So first of all, the definition of flux is Q inside over epsilon naught. What's the charge inside of here? It's zero. There is no charge there. Okay, so therefore the flux is zero. Another way of looking at it is whatever electric field comes in is also coming out. It has no choice. Okay? So back to my original question, what's the flux on this whole surface here? I add both of my charges. What is minus Q plus Q? Zero. So what's my flux in and out of this? Zero. Okay, very good. If I were to ask you this question here, rank these based on their flux. Which one has the most flux? Think about it for a minute. I want to hear some answers. Which one of these five has the highest flux? B and who? Will have the same flux, and are they higher or lower than the others? Okay. So absolutely, we got an answer. It's B has an equal flux to E, and because they have the highest charge enclosed, they're going to be greater than the other ones, which are all equal to each other. So it's equal to A, it's equal to C, and it's equal to D. All right? Remember, for the flux, it really is only the charge inside that matters. All right, let's talk about a cube. I have a cube here, and I put a charge Q on the inside. I have to do this fast because my battery is dying, so please cooperate. And I have another sphere with the same charge Q inside. What can you say about the flux coming out of the sphere and the flux coming out of the cube? Yeah, we have. Okay. Genevieve, what do you think? So she's got the right idea. I see what you're going, but ultimately it doesn't matter because with all the angles and the extra surfaces of the cube, they cancel each other out with the sphere. Ultimately, it's the charge inside that matters, regardless of our Gaussian surface. The charge inside is the same, and the flux coming out is therefore the same. If I were to ask you a different question, though, in my cube example, what is the flux coming out of only one face of these of the six faces? Exactly, and epsilon. Yeah. So the flux through one face. So the flux through one face is equal to 1/6 of Q over epsilon naught. Okay. The total flux is the same. It's just the flux per face. So now you have to divide that by 6. If, so maybe to expand on what Gabriel was maybe hinting at, is if this wasn't a cube and not all the sides were the same, would each face have the same flux? If let's say this was a rectangular prism, would each face have the same flux? No. Then you got to do a proportion of the areas to find it out. Here, answer my question. The total flux through the below spherical surface is? You shouldn't even need to look at the options. Tell me what it is. 0. Because what's the charge inside? 0. Also, electric fields come in and come out. They're all gone afterwards. Let's call it. Have a great day.